So we are continuing with geometric unity. I would like to correct a small mistake which I made previous time with the calculation of the signature, and I would like to make one further remark on the Zorro construction. Okay. That's the metric which we calculated previous time. As you can see, it's here, and this is correct, but this step was incorrect. This is not a diagonal matrix, right? This contains the cross terms. So explicitly we would say that basically say that G mu nu and G alpha beta D G mu nu dg alpha beta is equal to such kind of matrix, right? Matrix product dg00, dg11, dg22, dg33 times the matrix 1 minus 1 minus 1 minus 1 minus 1 minus 1 minus 1 1 1 1 dg00, dg11, dg22, dg33. Okay, but this matrix, yeah, it's not diagonal, it's clearly proportional to the projection operator. On the vector minus 1, 1, 1, 1, right, in this subspace of diagonal tensors. So it's easy to see, it's easy to find its eigenvectors and eigenvalues. So eigenvector obviously this is one of them with eigenvalue 4, and all others will have eigenvalue 0 orthogonal to this one. So for example 3 1 1 1 and then 0 say 1 minus 1 0, and the last one I could choose for example to be 0 1 half 1 half minus 1, so that they're all orthogonal to each other. And if they're all orthogonal to each other, we could make them orthonormal, and we could build a matrix out of them, right? Matrix C, such that C transpose times C equals 1 out of these 4 vectors, if they're properly normalized. And that's allow us to diagonalize this matrix certain basis. Say we introduce dg tilde mu mu as C times dg. Yeah, I guess the right way to write it is mu 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 mu, something like this. And therefore the total metric will look as follows. In the new coordinates we will have got for a sum over I less than j, dj ij dj ij minus for a sum over I dj 0I dj 0I plus 2a dg 00 dg 00 plus 2a sum of I dgii dgii tilde, and finally the last term will only contribute to one of the diagonal terms. Let's call them, without loss of generality, call them 0. dg 0 0 dg 0 0. Therefore we got, if a is positive, we get for the signature, right, on dg mu nu, we'll have for all the terms here dg 0 1 g 0 2, we always have minus sign. Here we have oh sorry, so on this 3 we will have always plus signs in our contribution to signature, and on these diagonal ones we'll also have always positive ones, plus 1 plus 1 plus 1, and this one dg 0 0, it will depend on the sign of 2a plus b. So if b is negative and negative enough to be to make this thing change sign, this will become minus 1. If it's positive, that will give us plus 1. So in total, if we count, this gives us 3 pluses, and this, so in total 6, and this gives us 3 minuses, and this will give us either plus or a minus. So if we're getting either 7 3 or 6 4, and if we reverse the sign of a, we also could get 3 7 and 4 6. So that's what Eric has. So now we reproduce his result, so it's all correct. It all matches. Well, as I said previously, I don't think it's that important because it seems like he has to complexify his fibers anyway. So I'm not sure that's anyhow relevant, but still at least we know that he doesn't have any mistakes here. Now also I would like to make a comment about the Zorro construction. I thought about it more. It's still kind of very weird, but essentially he's saying, let's say we have our manifold X of like dimension 1 3, and you have this Y above it, and he now chooses the metric on X, let me call it G, and that gives him Levi-Civita connection G on x13, and that indeed leads to covariant derivative on symmetric tensors sim square t star of x. And y is an open subset inside this cotangent bundle, or the symmetric power of cotangent bundle, because it's spanned by a certain open condition, right? The metric has to be positive definite symmetric tensor. But as this condition open, the Levi-Civita connection extends well on y, or let's say restricts well. So we are getting some sort of connection on y. And as you already know, having connection on y, we could build a metric on y, and using metric we could have spinors. But physically, it's not clear why we need it. In his Oxford lecture, Eric was trying to sell it as a feature that we don't need to pick a metric on x, we only pick connection on y, and that gives us metric on y, and that allows us to work with y as our metric space, to have spinors on that, to bypass all the standard problem of potentially quantizing the Lagrangian with two tensor, symmetric tensors. But he kind of gives up on it by doing something like this. So I don't see the meaning of it. He doesn't quite explicitly say that he means what I mean here, but that's the only way I see. And I don't know whether it's what he wants and why do we want it. So let me go back. Look. For example, yeah, that's the place where he does it. That's how he explains it. The importance of this is that each observation of y with a choice of metric I on x actually induces a metric and a connection on y, and then defines the topological spinors with the metric spinors. We don't have the spinors until we have some metric on y, for which we need connection. This allows somewhat more confidence to explore the idea that the metrics are not even necessarily present on y unless when observed with active observer under pullback I star. Further, if the problem with much of quantum gravity turns out to be the difficulty of quantizing metrics relative to other fields such as vector potential, this exercise allows us to move to more conducive variables for those who harbor dreams of quantizing gravitation. Well, not really, because that's now our dynamical field, right? It still have metric. He has to choose it. This is a bit strange. It should be pointed out here that the most possible metric on y are never in play. The subset of metrics that we are considering are incredibly tightly constrained and are equivalent to the space of connections that can arise on x as Levi-Civita connection, as opposed to the space of all metrics over y. Thus, the issue of what upstairs gravity waves are possible doesn't arise as the space of relevant fields is downstairs on x. Yeah, okay, but that's bad enough, right? He basically says, oh, whatever these weird connections are on y are parameterized by matrix of x. Well, okay, but how do you write quantum theory for some metrics on X. He doesn't bypasses any problems like this. Okay, so that's the signature paragraph which we already talked about. Yeah, so that's the place where he reiterates it. Yeah, we now assume how there's a distinguished choice of connection. Yeah, again, he begins with metric on X, determines connection on bundle Tx, yeah. The connection determines the metric. Again, here he keeps this unclear step, which I have to guess. And this gives him level with the connection. So that's, I guess, our dynamical variable. So with all that, we could go back to Lagrangians. Yeah. Give me a second. Okay, let me continue. So the problem, okay, that now becomes more clear what he means here. This is the usual pairing of one forms. And here in brackets he has this expression. This part is still unclear. I still wasn't able to figure this out. This, I guess, is the curvature of the connection F on B, and still it's not clear how he could obtain Einstein equations from it. On which variables? On a four-dimensional metric, or on some weird combination of metric and this one form omega? That's not clear.